What amazing device can transmit information at the speed of light, create beautiful displays of colored light, and also illuminate inaccessible places like the inside of your body? All of these things and more can be accomplished by fiber optic cables. Fiber optic cables transmit beams of light without allowing any of the light to escape until it gets to the end of the cable. How does this process work? To understand it, you first need to know something about how light bends when it passes from one material to another, a process called refraction. Whenever light passes from one material into another, it changes speeds and bends. You've probably noticed this before whenever you try to look at something underwater. Imagine that you look down into a clear lake and see a fish under the water. If you try to reach down and touch the fish, you probably will miss it, even if the fish doesn't move at all. That's because the fish isn't really where it looks like it is. Because the light reflecting off the fish's body bends as it travels from the water to the air, your eyes can't really tell exactly where the fish is. Snell's law allows you to calculate exactly how much a ray of light will bend when it moves from one material into another. To use Snell's law, you need to know what the index of refraction, or N, is for each material. The index of refraction tells you how much the light's speed changes in that material, and therefore also how much it will bend. Materials with a higher N will always bend light more than materials with a lower N. Snell's law tells you how much a light ray will bend if you know the initial angle that the light hits the surface, and the indices of refraction of the two materials. If light moves from a material with a higher index of refraction to one with a lower index of refraction, or N2 less than N1, the angle of refraction will always be bigger than the angle of incidence, meaning that the light will bend towards the interface between the two materials. What happens if the light bends so much that the angle becomes 90 degrees or even larger? In that case, no light will actually be able to travel out of the material it started in, and it will instead be reflected back. When this happens, it's called total internal reflection. You can rearrange Snell's law to find the minimum angle at which total internal reflection will occur. This is called the critical angle. What would the critical angle be if a light ray was traveling from glass, or N1 equals 1.5, into air, or N2 equals 1? The answer is 41.8 degrees. This means that if any light coming from inside the glass hits the interface between the glass and the air at an angle greater than 41.8 degrees, no light will escape. Instead, it will all bounce back into the glass. So how does all this apply to fiber optic cables? Fiber optic cables work because of the principle of total internal reflection. They are typically made of glass or plastic, materials that have a higher index of refraction than the surrounding air. Therefore, if light hits the sides of the cable at an angle greater than the critical angle, it will be bounced back into the cable. This happens many times along the length of the cable until it comes out the other end. Because As light travels so quickly, this seems to happen almost instantaneously. When light passes from one material to another, it slows down and bends. This phenomenon is called refraction, and each material has a specific index of refraction, or N, that tells you exactly how much the light will bend. Snell's law allows you to calculate the angle at which light will emerge when it passes from one material to another. And it also tells you that when light passes into a material with a larger index of refraction, it will bend towards the interface between the two materials. If the light ray hits the interface at a large enough angle, then all of the light will be reflected back. This is called total internal reflection, and you can arrange Snell's law to calculate the critical angle at which total internal reflection will occur. Fiber optic cables work because of total internal reflection. Light is sent into one end of a glass or plastic cable at an angle large enough so that it will not be able to pass out of the cable into the surrounding air. Instead, the light is reflected back over and over because of total internal reflection until it emerges at the other end of the cable. Fiber optic cables are used to transmit data and to illuminate objects in areas that are hard to get light to.